Hey guys, my name is Rodrigo, and let me introduce you to my 431 project. I would first like to apologize on the fact that the video quality isn't great. I'm having some terrible luck with camera for some reason. Um, so for my project, I don't know if you guys remember from the first day of class, Tina mentioned these temporary tattoo circuits that could actually be used for medical applications. The way it would work is you would put the tattoo on your skin like a temporary tattoo from when we were kids, and you would put it on the part of the body that you want to diagnose, which would be great because if you've ever been to a hospital, a lot of the equipment that is used to do that can be very intrusive. So I thought this was a really interesting idea. So for my part, I wanted to look and to see what kind of things are actually involved in this patch, or what kind of circuitry is involved. And you'll find that in it you'll find an amplification stage, noise reduction, and overall it would be sent to an electronic of any choice, like maybe a cell phone or a laptop. So let me show you my circuitry actually. So yeah, so here's the big network, and it's actually very straightforward. Again, the signal would be read in from the patch from the tattoo, and it would go through here. It would first see this amplification stage, which the resistor network here is to bias the amplifier in the middle of the transition region so that it can provide amplification. I designed this amplifier based on the assumption that I could provide 1.2 volts and 50 microamp hours. So the challenge here became that I am using a I'm using a differential amplifier with active loading for as PMOSes, and I need a current mirror to make a specific current flow through the amplifier. The problem with this is that I have a total of three transistors stacked on top of each other, and in order for the amplifier to work as an amplifier, these transistors have to stay in the active region. So, in order to guarantee that, you might recall from class, Tina went over some math that lets you actually lower the saturation voltage of a transistor by appropriately providing a ratio between the width and the length of the channel in the transistor. I believe you have to raise the width to make the saturation voltage smaller. I could be wrong, but either way, for a 1.2 voltage supply, I just evenly divide the voltage across these transistors and make the saturation voltage as small as possible to guarantee that this amplifier stays in the active region. Other than that, the reason I chose this is because I needed a gain of around 50, and this was probably the simplest architecture I could implement that could provide a gain of 50. So yeah, after this amplifier, any sensor should be able to read in the signal and do stuff with it. But for now, the output of this amplifier actually goes onto what's called the 20 notch filter. Um, this is a this is an EE409 concept, which I'm sure maybe a lot of EEs are familiar, but if you're not, a 20 is basically the same thing as a notch filter, where if you recall from 212, a notch filter lets you block specific frequencies from coming in. Um, for this case, I wanted to block 60 hertz noise because that's probably going to be the most obstructive noise in an implementation like this. So the other thing is the reason I wanted to use a 20 notch instead of a regular notch filter from EE212 is doing it this way lets me emulate an inductor using components such as a capacitor and resistors. I don't want to use an inductor if I were to actually implement this, because as you know, inductors are very bulky. And if you would imagine someone actually wearing this uh, tattoo on their skin with an inductor, it would be very uncomfortable because a lot of the inductor would take up most of the area on that patch, and it would just it would be very noticeable. And I don't think a lot of people would enjoy having something like that on their skin. So again, it's just the reason I use the twin T notch filter is to avoid using inductors because they're big. So the output of this notch filter would go to an ADC, which my partner Juan is creating. So I would recommend watching this video if you have time. Other than that, that's pretty much it for the circuit. It's very straightforward. This is probably the easy part of my project, but there is one major flaw in all of this design, and that's has to do with this capacitor, which has made things very complicated. You see, this capacitor was originally used to get rid of the DC offset that would go into the amplifier. The problem is a lot of the signals from the human body are very low frequency, which give me 1 second. So again, a lot of the signals that come in from the body are very low frequency, and in order for the signal to make it across the capacitor, it has to see it as a short. So at best, let's say the signal that comes in is 100 hertz. In order to make that capacitor look like a short, as you recall from the impedance of a capacitor, which is 1 over omega c, if my frequency is 100 hertz, in order for me to make that impedance look like a short, I have to increase the capacitance. I found that an ideal capacitance that would let an 100 hertz signal come through can be in the order of microfarads, which may not sound like a lot, but in silicon you can draw squares that give you attofarads per, I believe, nanometer. The point is that if you were to actually draw a microfarad capacitor, you'd find that you'd need a lot of area to make just the capacitor, and the result would be that your whole temporary tattoo would be just that single capacitor, which is very impractical. So the challenge then became trying to find a way to read in the signal without having to use this capacitor. And after talking to Tina, what we came up with was, if you use two coils